Okay, so carbon is the backbone molecule of all organic compounds and therefore all biological compounds. So it forms four bonds, which is the most any element can form. It has, it's right in the middle of the periodic table, relatively speaking, and so it has properties of both metals and nonmetals. It's relatively unreactive. So it makes a great building block kind of atom to structure molecules around. And it's also good for storing energy in its bonds. The carbon-hydrogen bond in particular has a fair amount of energy in it, and we use it for that as well as for building blocks for all our biomolecules, etc., and all other organisms. And so one of the two of the main biotic processes that take place, and it's really just an exchange, they are photosynthesis and respiration. So we have the formula up here, or the equation, I should say. Written like this, which process is this? Photosynthesis or respiration? Respiration is correct. Oxygen is going in. Now, so you got your glucose here. So we eat that in one form or another. Breathe in oxygen, break it down, exhale CO2 and H2O in the atmosphere. So now go like this, look at it like this, without falling over. Now which form is it? Just that. Now which process is it? Going this way. Photosynthesis, right. The exact same equations reversed. Okay? So it makes a nice little convenient exchange back and forth between respiring organisms and photosynthetic organisms. And consequently, both can get fed, and both can get biological molecules or building blocks. In the case of plants, they can get their inorganic building blocks of carbon dioxide and water back. And do the whole process all over again. So this is, like I said, this is the main biotic process in that. Let's look at it for a minute as pertains to spheres, transfer between spheres. So in photosynthesis, plants are going to take CO2 from where? Where do they get it from? What sphere? The atmosphere. Yeah, it's a gas, right? So that's one thing, carbon does have a gaseous phase. That's part of one of your examples or questions, pretest questions. So it's going to get out of the atmosphere and it's going to put it into what sphere? The biosphere, right, very good. By making biological molecules, glucose, and all kinds of other stuff from there, puts it in the biosphere. Cow comes along, eats that grass, exhales back out the CO2. Now it's going from the cowosphere, which would be the what? Biosphere, back into the atmosphere, right? Okay? So that's the example of how I want you to be able to see transferring back and forth between the spheres and the process that takes them from the one to the other. All right, so anthropogenic impact, remember number 4 over here, something we always want to look at. So you could substitute anthropogenic here, by the way. Nothing else digs up fossil fuels and burns it that I know of. And so we do that. We burn fossil fuels, and we also cut down trees, right? Both of those end up producing carbon dioxide. The fossil fuels, of course, because they're organic substances, anytime you burn an organic substance, you're going to produce carbon dioxide, amongst other things, because you're reacting with oxygen. Oxygen comes in and breaks the bonds in those organic molecules between the carbons and the hydrogens. So you have that, and then you have deforestation. Now, how's deforestation going to increase CO2 levels in the atmosphere? Yeah, Ms. Farkas.
Because the trees don't like accept the carbon dioxide anymore.
Right, very good. That's part of it. Is the fact that trees absorb carbon dioxide. They're photosynthetic organisms, and in particular, now of course all plants do that, but think about it, with trees, they absorb that CO2 and they build much more tissue and they grow bigger and bigger year after year. Okay, some of them for thousands of years. So every CO2 molecule that becomes part of that tree and does not get eaten and just becomes more tree, it means that carbon is not in the atmosphere. And why are we concerned with CO2 in the atmosphere? What environmental issue is that associated with? greenhouse effect or global warming, global climate change. Correct. CO2 is a greenhouse gas. The more that's in the atmosphere, theoretically, the warmer the Earth will get. All right, so deforestation. Another thing about deforestation, usually when they cut down these trees, they burn them. Okay, so that obviously, just like burning fossil fuels, is going to take it back into the atmosphere. Sinks. What's the sink for fossil fuels? Where is it? What sphere is it in? Lithosphere. So we take out lithosphere, release it into the atmosphere. Okay, that's part of the problem. We burn so many fossil fuels, we're taking them out of an area where they would not normally be out into the atmosphere as CO2, and putting it into the atmosphere by doing that, and therefore releasing it. Deforestation, we're going from the biosphere into the atmosphere. Okay. All right. Another factor in the whole carbon cycle, very important factor, is the fact that carbon dioxide is water soluble. That's what a soda is, like a Coca-Cola or a Sprite or something like that. Those bubbles are bubbles of carbon dioxide. Okay. They do that because carbon dioxide not only dissolves in water, but it reacts into what it does, and it forms CO2 plus H2O, a weak acid called carbonic acid. And acids taste sour, so therefore that gives soda its tart flavor and gives you the bubbly effect that's, you know, if you like that. So if you had two sodas, one was cold, one was at room temperature, which one do you think would go flat faster? Yeah, the one at room temperature, right? Because as it gets warmer, does the solubility of gases increase or decrease? Now, I'll tell you, when the soda bubbles, those bubbles coming out in the process of going flat, it's releasing its the CO2 is undissolving and coming out. So how soluble it is, how likely it's to stay in that solution, what relationship does that have with temperature? Does it decrease when it gets hotter, or does it increase? Decrease, very good. It's less soluble. And this is not only true of carbon dioxide, it's true of oxygen, ammonia, whatever other kinds of gases might be dissolved in the water. They are inversely related to the temperature as far as their solubility. And you guys may remember that I mentioned the fact that we don't have trout in Florida. One of the reasons is our water gets too hot in the summer and loses all its oxygen. Plus we don't have a lot of turbulence as well to stir it up. All right, now let's look at this interaction again. CO2 plus H2O yielding carbonic acid. So when an acid is in water, it's dissociated, it's dissolved, so that CO3 is going to exist as a carbonate ion. And then the two H's will go off and they'll react with water molecules to make H3O plus. I don't get into the details of acid-base chemistry right now, but that carbonate ion dissolved in the water will then be potentially absorbed by shell-bearing marine organisms like reefs, like clams, oysters, etc. They will react it with calcium to make what compound? These two compounds. This one was this one. What's this one called? Calcium, and this one's called carbonate, calcium carbonate. Okay. Now you may remember on the pretest there was a question asking about, let me read it exactly. Which of the following process is a process that indirectly removes carbon from the Earth's atmosphere? And the correct answer for that one was, 23% of you got that, formation of carbonate deposits. Okay, so that's carbonate. It's going to react there. Now you could technically say it's part of the biosphere. It's not really a living substance when it's a shell, but you could say it's part of the biosphere while it's part of that organism. But eventually, it's just going to sink down to the bottom and form what is on the bottom down there? Sphere. What sphere? What's it going to be in there? It's going to be the lithosphere. Okay, so going down, sinking down to this lithosphere is going to be your lowest sphere, basically. And so consequently, like I said, the question asks, which of the following processes is a process that indirectly removes carbon from the Earth's atmosphere. So here's the thing, CO2 naturally dissolves in the oceans, but it also gets released from it. That's what it says, it regularly absorb and release CO2, just like a soda pop. You open it up, there's CO2 in there, there's actually an equilibrium that establishes between the surface of the soda as it goes back and forth between it. Same thing with the oceans and carbon dioxide in there. One of the things that will determine how much carbon dioxide that ocean will hold, besides temperature, is how much carbon dioxide is already in there. So if the shells take it out, the reefs and all the shell-building organisms take it out of the ocean water and bind it up as calcium carbonate, then that means there's more room for CO2 in the atmosphere to be absorbed back into the ocean water. Does that make sense? Yeah, kind of, a little bit. We'll draw a diagram. Should I give them? Sure. Bye. Ms. Wheel, you are checking out. All right, so carbonate formation, also sometimes carbonate sedimentation, sometimes it's called, or calcification. There's a number of different terms for it, but just know that it does pull the CO2 out of the water, and therefore that makes more room for CO2 to come out of the atmosphere and go into the ocean. Any questions about the carbon cycle? All right, so nitrogen cycle. Nitrogen, about 78% of the nitrogen is in the atmosphere. Therefore, most of the nitrogen in the world is in the atmosphere. However, it is present as into gas, which is an inert gas. And that means it's also not available to most organisms, and plants can't use it in that form. And we need nitrogen, so plants can absorb nitrogen, and it's either oxidized or what we call reduced form. And you'll notice I've got an X here. That's because that can be a nitrite ion, NO2, or it might be a nitrate ion, NO3. So you can absorb either one of those. Some plants can absorb the ammonium ion. And you may have noticed the difference there between ammonia, which is a gas, and ammonium, which is a dissolved ion. The ammonium form with the 4, NH4 instead of NH3, is what plants can absorb. And that's what they can do. So like I said, some of them can do that particular process. And I forgot to put some in here, so y'all make sure you pay attention and add it on, make a note on your, if you're not keeping along, but make sure you put it in beside your other notes or something. But bacteria can do chemically almost anything, seems like. And there are bacteria that live in the soil, and they also live in, some of them form symbiotic relationships with plants. You saw the picture with the bunny and the plant that had the funny looking roots. Anybody know what those roots are, what those little things on them are, or what the significance of that is? They're called, okay, good. Well, not so good, but we'll see. Those are nodules, and inside of those nodules live these bacteria that do what we call, good guess, group 2. That's not the one, though. I mean, that makes sense, too. Unfortunately, it's not nitrification. It's called nitrogen fixation. I know, right? Why is the opposite of denitrification nitrogen fixation? I don't know. I didn't make up the names. But in general, when we talk about fixing something in ecology, it means we're taking an element that's out in the environment, in the physical environment, and incorporating it into living tissue. So, or at least making it a form that can be directly incorporated in living tissue. So they call what nitrogen fixing bacteria, what bacteria that take nitrogen out of the atmosphere and put it into a form that plants can use. They call that nitrogen fixation. There's an opposite process where bacteria in the soil will take nitrates, nitrites, and ammonia and convert it back into nitrogen gas. So I'm going to give you guys a table of this, so don't worry about that right now, but it will be something you're going to have to commit some memorization to. Okay. So we have that process, and again, that can get into the plants, and plants, and therefore the nitrogen can get into the food chain. And then when we excrete, we tend to generate ammonia. And you know that from the smell of urine. Now it's actually not, it's actually in a compound called urea, but then the bacteria act upon it, they produce ammonia. And like I said, some plants can use ammonium is what I should be saying, ammonium. But majority of them cannot, so we have another process that is called nitrification. So you have to write this in. Like I said, I'm going to give you a table on these, so but just so you know now. So nitrification will then take ammonium and make nitrites or nitrates out of it. That's why we're going to use the NOx there. Okay, I know it's complicated, but some of the things that just to keep in mind that a lot of these processes, like many things, are done in the soil by bacteria. And you can commit yourself to memorizing the different names of different processes later. Like I said, I'll give you a table to do that. But most of the nitrogen on Earth is in the atmosphere. However, most plants can't use that, so we have to rely upon bacteria to convert that into nitrates or nitrites or ammonium, which can then be used by plants. What do we do? How do people impact the nitrogen cycle? One thing, we make a lot of fertilizer. As a matter of fact, one of the things that led what we call the Green Revolution, where farming became industrialized, was the ability to produce chemical nitrogen-containing fertilizers. So, excuse me. So we do that. We produce a lot of fertilizer. We use it, and we'll see in a minute what happens to that when we do that. Also, excuse me. Even though nitrogen normally is unreactive under the high pressure and temperature of either internal combustion engines like we have in automobiles or certain factory processes or power generation plants, under those conditions there is reaction of nitrogen with oxygen. It also naturally forms, nitrogen oxide compounds naturally form from lightning strikes in the atmosphere. So that is that can get into the water cycles. We'll see here in a minute. So those are some human impacts there. The excess nitrogen, form of nitrates or ammonia or nitrites, I'm just going to say nitrogen in general, from fertilizers, oftentimes ends up in waterways, lakes, ponds, rivers, etc. And they cause something called cultural eutrophication, which is an overgrowth of algae and bacteria in a body of water. Now, I noticed a lot of people got that wrong on the pretest. I thought I'd probably mention it by now. This particular word you will know very well by the time we're done with this course. This is the most common type of water pollution problem, and we have a lot of familiarity with it in this area. Lake Apopka is highly eutrophic, and if you've ever been there on a summer day, you'll see what I mean. It looks like pea soup. The Indian River Lagoon, over the summer, experienced one of the problems that happens when these algae bloom. The algae blooms out of control, and then it crashes. Well, like they do, they're what we call an R-selected type organism, and then the bacteria eat all the dead algae, and that saps the oxygen levels out and kills a bunch of fish and other organisms that need oxygen. So there's all kinds of environmental consequences that happen from this chain of events. It's a pollutant, but it's not actually, they're not poisonous. They just overburden the ecosystem with nutrients, and the algae takes off on it, and then from there the bacteria as well. So we'll become very familiar with that particular process in the future, but you should know a little bit about it right now. And then another thing, these nitrogen oxide gases that are produced during fossil fuel combustion are one of the components of acid rain. We'll talk about how that happens. These nitrogen oxide compounds react with water vapor molecules, or the water molecules, excuse me, in the clouds and form nitric acid. So that's one of the components of acid rain, not the main one, but one of them. All right, any questions about nitrogen cycle? This is a really complex cycle with dozens of actual reactions that take place. There are entire semester courses in college devoted to that particular process. But we're going to just kind of scratch the surface right now. All right, then phosphorus, sulfurous, and micronutrients. Kind of a catch-all bag there. Phosphorus important. It's a major component of nucleic acids, bones, and shells. Okay. They use it in fertilizer. Your main ingredients in most chemical fertilizers are nitrogen, phosphorus, and potassium. Detergents, at least they have in the past. Some of that has been banned because of the problems it causes. And other products like explosives and things like that, they use phosphorus as well. A lot of different things. Florida is a big phosphate mine. Actually, the Florida, I believe, in the United States is the #1 phosphate mining state. A lot of people don't think of Florida as having mines, but we do. We have a lot of phosphate mines. Do you have a question, Mr. Nelson?
Yeah, what's that first, like to say? Bones?
Them bones. Calcium phosphate, main component of your bones. All right, one of the things that's interesting, and I will say this, they tend to ask this a lot on the national exam, is the fact that there's no gaseous component for phosphorus, at least in the phosphorus cycle, so nothing common. You can make some in the lab, but in general in nature, you don't find phosphorus in the atmosphere in any form. Just doesn't make those kind of compounds simply. Another part about phosphate, another property of phosphate that's important, is that it is insoluble, as in not soluble, in water. Okay? So that means phosphorus typically spends most of its time in the lithosphere. And we tend to dig it up, or you have natural erosion and things like that take place that'll get it out there and available and spread out, and it can be absorbed by plants. I'll talk to you guys later about how plants can take insoluble compounds and make them soluble so they can absorb them. But in general, it tends to stick with the lithosphere. And because of that, this is one of your questions, it becomes a limiting agent a lot of times, or limiting reactant a lot of things, because it's usually in short supply for a lot of ecosystems. Which is good though, actually, because anytime you have an excess of something, you have certain parts of the food webs that'll go out of control, like in a eutrophic lake. So, consequently, it is, like I said, limiting reactant. It does find its way. It's a component of eutrophication, and we'll speak about the dynamics of that much later when we do water pollution. But it, along with nitrogen, are your two main elements that contribute to the eutrophication process. All right, sulfur. We find sulfur in proteins. Like the kind of proteins you find in beans. How do you know that? What are beans good for? Your heart, right? What do? What do they make? Yeah, particularly stinky gas. That is because they are high in sulfur. Broccoli and cabbage and your cruciferous vegetables as well, which is good. You need that. That's why they're some of the most nutritious things you get. But that is what ends up being converted into hydrogen sulfide gas, which is the gas that is responsible for the odor of flatulence and sewage and all those other kind of nasty things. Okay. We release it a lot during mining. Burning fossil fuels, particularly coal, can have a lot of sulfur in it. And this is the #1 cause and component of acid rain, sulfur oxide. So particularly burning coal that's high in sulfur is a reason why we get acid rain. And finally, last one here, micronutrients such as iron, magnesium, zinc, manganese, a whole bunch of them. They're in small amounts, but they may be a limiting factor. Citrus trees, for example, need manganese. When they first started discovering them in the Andes soil typically has a lot of manganese in it. They couldn't grow them in other areas until they figured out it was the manganese that they were short of and started supplementing. If you get citrus tree fertilizer at your garden center, it has manganese in it. So missing ingredient, so to speak. So you can have one small ingredient. If it's not there, then they may grow but not fruit, for example. Any questions about your nutrient cycles? Yeah.
That one right there.
Which bottom one, right?
The third line in the first paragraph of the.
Go up there, please. I'm never going to